Prescott, and she'll be talking about extended gaseous nebula around fading AGNs, and she's from New Mexico State University. Take it away.
Great, thanks so much. So yes, I'm talking about extended nebulae around fading AGN, and let me know if you can't hear me or can't see my mouse. I think this is working. I'm talking about work that I'm doing with my grad students, Kelly Sanderson and Audrey DeJoe at NMSU. All right, so extended emission line nebulae are really interesting regions because they give us spatially resolved information about the kinematics and physical conditions in the circumgalactic medium. And here I'm talking about out to tens or even hundreds of kiloparsecs. And at the same time, they have the potential to give us insight into what the ionizing output of the central AGN may have been tens to hundreds of thousands of years into the past. And so a local example of this is in Hannes-Vorwerp, which is shown here, where this extended nebula shows us that the AGN in this galaxy has ramped down significantly in ionizing output. It's basically left behind this ionization echo. And this has been done for a number of other sort of local systems where you can see this mapping the output of the AGN versus distance, which corresponds to a light travel time, showing this kind of ramped down behavior. So there's a lot of power in using this extended gas to probe the ionization histories of the central source. Now, the most dramatic cases of these extended nebulae that we have are at high redshift, where they've been found via their Lyman alpha emission. So here I'm talking about 100 kiloparsec plus nebulae. And here's just some examples from the literature. And Lyman alpha is key at high redshifts because, well, it's a very bright line, but also it conveniently redshifts into the optical above redshift 2. So they're often just called Lyman alpha nebulae. And these really luminous, gigantic cases, they're very rare and they seem to be confined to dense environments. So likely where groups and clusters of galaxies are forming. But more recently, of course, we now have sensitive IFUs like MUSE on the VLT and the Keck Cosmic Web Imager, which are letting us see to lower surface brightnesses out of these high redshifts. And they're revealing, basically ubiquitous, fainter Lyman alpha nebulae around high redshift galaxies generally. And so this is, again, a real opportunity to map out kinematics and properties over circumgalactic and in some cases even intergalactic scales. So some of the largest systems, are above 500 kiloparsecs in size. And here I'm just showing an example from some work that my student Kelly has been doing using MUSE observations, looking at the morphology and the complex velocity field kinematics of a Lyman alpha nebula at redshift 3. All right, but of course at high redshifts, we're dealing with higher surface brightness dimming, and it's more difficult to get multiple line constraints that we really need in order to really understand what's the conditions in this extended gas. So there's an incentive to move actually towards lower redshift. And luckily, we now have a sample of 17 of these extended nebulae at redshift 0.3. And these have been dubbed the green beans, because they are very luminous and extended in oxygen 3 507 emission. And so this gives them very large sizes and greenish colors in the Sloan imaging. So here's an example of one of these green beans that was discovered by Shermer et al. And as I said, they're picked out because of their somewhat unusual colors. So for example, in this G-R minus I color plot, you can see the green bean sample here sitting in this kind of weird place, offset from the locus of other sources. And so not only are these extended green beans O3 nebulae, they are they show an excess in far UV emission from existing GALEX coverage. So at this redshift, I should say, the Lyman alpha emission line is sitting nicely in the FUV band. And so this suggests that these green beans are actually Lyman alpha nebulae, similar to the ones I was just mentioning at high redshift, but now at much lower redshifts where it's a lot easier to study them. They are very rare. There's only 17 in the Sloan survey. But there's evidence that they are, in fact, ionization echoes, like I was talking about. They're echoes around fading AGN. And the argument there comes from plots like this one, showing the O3 luminosities versus the measure of the infrared luminosity, where we're here infrared luminosity, we're taking a sort of a measure of closer to the intrinsic current power of the system. And so the finding that the O3 luminosities, which is again coming from, spanning larger light travel times across this nebula, the fact that the green beans all seem to be elevated in O3 luminosity compared to other AGN samples at similar redshifts. This is suggesting that we're seeing sort of a evidence of a previous era when the AGN was much more luminous, leading to this extended O3 emission, and has since ramped down. So we got interested in looking at these this sample of low redshift Lyman alpha nebulae. And APO is ideal for doing this kind of work, for following up extended nebulae at redshift 0.3. We're using both the low and the high resolution, or medium resolution, I guess, mode on the DIS instrument. We started with a pilot sample and have since expanded to cover the entire sample of green beans. And so we're hoping to get a good emission line constraints for a suite of emission lines. And this is just one example here with the blue and the red side. Of course, with the O3 emission line, that's the most the brightest feature, and gives us a lot of information about the spatial extent as well. And so the first thing we wanted to go after was just a simple question of how did these green beans relate to other extreme emission line sources in terms of power source kinematics and their emission line properties. So we started off by making a classic BBT diagram. So here is, for example, the O3 over H beta, N2 over H alpha panel up in the left here. And I'm showing the green beans here as stars as compared to another sample of type 2 AGN at similar redshifts, and also a sample of compact, highly star-forming galaxies, whimsically named the green peas. So here you can see that the green beans are indeed up in the upper right of this plot, in the AGN portion of the diagram, well above sort of the canonical division line between the star formation powering and AGN powering. And so, as we sort of suspected, these are AGN powered systems. And in addition, we can look at look for any evidence of broad widths on the permitted lines, but we don't see that. We see relatively narrow widths. So this, for example, is just the H beta full half max measurements showing these are type 2 systems. So these green beans are powered by type 2 AGN. And then we wanted to look a little bit more carefully at some of their other emission line ratios. And so, for example, we wanted to ask, is there anything special about these green beans compared to just your garden variety type 2? So for example, we looked at the neon 5 to oxygen 3 ratio, where neon 5, very high ionization line, even compared to the O3 line. So this is giving us kind of a proxy for the hardness of the ionizing continuum. And so I'm just plotting that versus infrared luminosity. But you can see that the green beans here on the stars, nothing really unusual here. They're fairly typical in terms of their ionizing continua compared to your garden variety type 2. We also wanted to look at, is there anything special kinematically? And so for that, we looked at the emission line profile shapes. So for example, here are just some examples of the O3 doublet profiles for a set of type 2 AGN from the Yuan et al. Sample, where you can see asymmetries, double peaks coming from the kinematics of the gas. So we basically took some non-parametric measures of the kinematics encoded in the line profile shapes of our sample, and compared them between the green beans and other type 2s. And so these panels here are just showing different non-parametric measures of the velocity widths measured in different ways, the asymmetry of the line, kurtosis of the line. Bottom line is we don't really see significant differences other than maybe a hint of lower kurtosis, meaning sort of weaker tails on the emission lines in the green bean sample. But overall, broadly similar as a continuum and similar kinematics to other type 2 AGN. So we were kind of looking for what makes these green beans special, and so far we kind of haven't found much that's really makes them stand out. So we wanted to go back to, okay, why were they selected in the first place? They were selected because of their extreme colors. So let me go back to the color selection. So this is a G minus R, R minus I plot. And you can see that as compared to, the type 2 sample I've been looking at and the compact star-forming galaxies, the green beans by definition are up in the kind of upper left part of the diagram here. That's how they were selected. And that's coming in part from their very strong O3 emission. O3 equivalent widths are very high. And we can show that with our, now with our spectroscopic measurements. The equivalent widths of O3 are scattering to the high end compared to sort of what you see for typical type 2 AGN. But that's not the entire story. There's also some differences in the continuum. So when we took our disk spectroscopy, we created a stack of just the green beans, and then independently for the type 2 sample and the compact star-forming galaxies, and we show that comparison here. So you can see that the green bean stack is relatively flat in F lambda compared to the type 2 AGNs, which are a little bit redder in underlying continuum. And we can check for any differences in dust attenuation. There's not really any differences there. The Balmer decrements are similar between the two populations. And as I mentioned, we didn't see evidence for any broad components on the emission lines, suggesting it's not a result of AGN scattered light. So it really does seem like there's some differences in the underlying galaxy stellar population in this green bean sample. However, we wanted to look at this more closely because it turns out there may be just some biases that are creeping in here to give us this result. We wanted to understand kind of what the original selection was doing in terms of selecting these objects. So this is work that Audrey Dejoux, a student at MSU, is leading, where we're taking simulated emission line nebulae and just sort of seeing where they fall in the selection space. So for example, this is a G minus R, thank you. G minus R versus R minus I color plot. And all of these little colored points here are simulated nebulae at a range of redshifts. So the redshift here coded with these colors. And a redshift 0.3, those are systems that have kind of this magenta color that tend to be in this part of the diagram. And so you can see that, for a range of equivalent widths, a range of continuum slopes, these simulated nebulae fall all throughout this diagram. But as you dial up the O3 equivalent width, not surprisingly, at this redshift of 0.3, systems are then heading into this upper left part of the diagram. However, the continuum slope is also important to the color, of course. And so for a range of continuum slopes, this is sort of where the simulated nebulae end up. And so what this means is that if we look at what the original color cuts were doing, that's what these gray lines here are showing. They were, in a sense, picking out high equivalent width objects, but also sort of in a restricted range of underlying continuum slopes, giving us sort of the bias toward flatter slopes that we saw on the previous slide. So what do we want to do? We're interested in improving on this. We're interested in revising the color selection to really isolate things that are all high equivalent width sources. And we're looking at combining Sloan imaging with DESI legacy survey imaging in order to redo the selection and efficiently remove false candidates. And so then we're looking forward to using APO to follow up to confirm candidates like this one here is a new candidate, and to extend the study of nebula properties across a less biased sample. And so with that, I will just wrap up. So we're using APO and DIS to study a rare sample of low redshift Lyman alpha nebulae, the so-called green beans, confirming that they're powered by pretty typical type 2 AGN with similar spectral ionizing slopes and kinematics, but with large equivalent widths of 0.3 and bluer optical continua in the existing sample. But since some of these trends are actually coming from the way the original selection was carried out, we're trying to improve that to identify a less biased sample. And we're looking forward to future follow-up with APO and other instruments, other telescopes to investigate the kinematics and conditions and ionization histories within these extended nebulae around low redshift AGN. I'll stop there.
Thank you. Questions, please. Generally, what do you think is the evolutionary phase that is causing these green beans?
Yeah, it's a great question. Sort of, what are they exactly? I mean, certainly morphologically, many of them appear to be sort of outflow structures, AGN outflow, but on very large scales. I guess there's a lot more work to be done, I would say, in order to really pin down exactly what's going on. Only one system really has been studied in detail. So I guess I would say stay tuned. I don't have a full answer to that yet.
Is there any correlation with some kind of alignment angle?
Well, that's actually interesting. So I guess in these systems, I can't really say. I guess they look like morphologically like outflows perpendicular to the galaxy disk. I can say that much from the optical imaging. My student Kelly is also looking at sort of related systems that are radio loud as well. So they have radio jets, and there you might be able to say something more about the alignment of the jet with the optical emission.
Well, I think we're done for this morning. Thank you very much to all of the speakers, especially to the students. Well done. And I'll hand it back over to Nancy.
Great, thank you. Yeah, so we're heading into a break, and I guess I just wanted to remind everybody that we're going to try our first GatherTown session at 12:30, which is a poster session. And what I'd like to do is ask everyone to meet at the APO logo once you get into GatherTown at 12:35, because we're going to try to take a group photo, all virtually, of course, but we're going to try to gather everyone all in one spot and see if we can get a picture of everybody while we're there. And then we'll continue on with the poster session. Right after that, we have one more oral session, and then we go back to GatherTown for some more informal discussions, including a meet and greet of some members of the APO staff if they're able to join us, and some other topical discussions of any choosing. Okay, so thanks everyone. We'll see you back here. At 1 p.m. Mountain Time, but we'll see you over in GatherTown about 15 minutes or so. And if you've forgotten the instructions, they're posted on the Slack. Thanks.